All right, back from break. So you can see that once we move into 3 dimensions, we see effects now that are much more realistic. We had finished up with this set of drawings of the different possible probability distributions for these wave functions in 3 dimensions. And we started to see similarities with the hydrogen wave functions. Now, in chapter 39, when we come back after the midterm, chapter 39, we're going to go in and actually look at the hydrogen atom and solve Schrodinger's equation, and at least for some of the wave functions, we'll get a chance to go in and see how they get derived. Right now, we're still working in rectangular coordinates, which are easier to work in terms of. In chapter 39, we'll come back when we're looking at atoms and work in spherical coordinates, which match the symmetry of an atom. So an atom is characterized by a central nucleus. Instead of having these sort of artificial walls that we've been using here, a cubic region where the particle is confined, it's more subtle. There's an electromagnetic force attracting the electron and the proton, and that electric field that's being generated and the electric potential energy is spherically symmetric, not rectangular coordinates. Anyway, something to look forward to after the break. But again, what we did was, just to quickly review here, what we did in the earlier hour is we started off with this 3-dimensional Schrodinger equation. So we had, since we were working in rectangular coordinates, we had second derivatives for x, y, and z, and we're using a Schrodinger equation, which means it's non-relativistic. So the energy formula here for kinetic energy is our old classical kinetic energy formula of momentum squared divided by 2m. So we were, with not too much difficulty, able to take a look at the 1-dimensional wave functions and extend that to 3 dimensions. And then we went through and showed that this 3-dimensional wave function that we tried as a test, as a possible solution, it really worked. And so when we plugged that wave function into the Schrodinger wave equation, we were able to establish that we had an eigenstate. We had a quantum state that had definite, or a series of quantum states that had definite energies, definite kinetic energies in those quantum states. So yeah, it worked. And then when we did the probability distribution here, and we started plugging in some of the simplest sets of quantum numbers for these wave functions, we could see that the distributions we're getting had similar appearances to s orbitals, p orbitals, and d orbitals. And if you've seen those, that's great. And if you haven't, we'll start talking about those in chapter 39. All right, after going through all the trouble of working in 3 dimensions and deriving a bunch of wave functions, here is kind of an interesting example going back and looking at the Planck distribution. Now, if you remember, the Planck distribution that we saw back in chapter 37, right at the beginning, with thermal radiation of photons, started with this assumption that we had, again, we could imagine in a container at a certain temperature, and the container inside has an equilibrium distribution of photons. So, you know, we're used to thinking, okay, I got a container, I have some gas molecules in there, or maybe I have some electrons in there. Well, this time it's photons. So we're looking at a distribution of photons inside there. Now, there's going to be a lot of similarities with what we just did in 3 dimensions, but there are going to be some differences. So let's take a look and see how this compares. Now, also, let me point out that this is not in the textbook, and it's not something that you are responsible for. So this is just, going through this will allow us to again, think 3-dimensionally. And instead of using the Schrodinger equation, because these are photons and they're massless, we have to use relativity. And so there's really no choice here whether to use relativity or not. And for a massless particle in relativity, the equations for energy and momentum are reduced down to E squared is equal to PC squared. Now I guess we could take the squares off, but officially we start off with this statement. And that says that we can substitute in some operators. Now, on the left side of the equation, for the energy, since these are quantum states confined to a region, I'm not going to stop and actually put in the energy operators. I'm just going to write down E squared. We've done that before. But on the momentum side, it's going to be important to put those operators in, because it's the momentum operators that are going to tell us how the wave functions are spread out spatially in terms of x, y, and z. So I put in the momentum. Now there's no mass, there's no potential energy here for these photons. So that's it. That's the whole story. This is what the wave function will look like based on relativity for photons. Now, I actually went and just took the wave functions that we saw before, okay, that one at the top. Here is the wave function that we were using to represent electrons, for example, or maybe some gas molecules inside this region. Well, it turns out we can take the very same wave function, and it is also a solution to this relativistic wave equation. Kind of interesting that we can use the very same set of wave functions. And the reason that works is they are going to meet the boundary conditions the same way that they met the boundary conditions when there were electrons inside. So photons are going to have the very same boundary conditions here, in that the wave functions have to go to zero at the edges. So I use the very same wave functions, plug that in, and if you remember, and I guess we can refer back here quickly, if you remember, here we go. Here was the wave function that we used for the electrons. And then we did second derivatives. Well, we're going to do second derivatives again. And so we're going to end up with kind of the same set of constants coming out to the front. So we're going to end up with those nx squared pi squared over L squared factors in front of the wave function. Now what is different this time is we don't have the I h bar, or the h bar squared over 2m that we had for classical kinetic energies. Instead we have relativistic momentum in that equation right there. And so anyway, we have factors of h bar c squared out front instead. So this is what the equation looks like. Now what I've done over here is we're going to take these quantum numbers one step further. We're going to take the nx squared, the ny squared, the nz squared, and think of them as n squared. Now, what does that represent? Well, first of all, we can simplify the energy equation down so it just says that the energy for a value of n is equal to n times hc over 2L. Now, that's a pretty simple formula. The hc, if you remember, is just 1240 eV nanometers. And then if we divide through by the number of nanometers, divide by a factor of 2, we're going to have all the energies. Now this little n that we've defined, that's a little complicated because the nx, ny's, and nz's, those are integer values. That guarantees that n squared is also an integer, but it doesn't guarantee that n by itself is. And so we'll see how we use this in the next slide. So let's jump ahead here. So what we've done is we've got all these photons inside this container. We're trying to find out what all the possible quantum states will be for those photons. And here's how we count. We actually go in and we count the number of possible quantum states for the photons. And here's the trick that we use. So what we do is we create a quantum state space. and it's based on these quantum numbers, nx, ny, and nz. Imagine, mathematically, creating a coordinate system for nx, ny, and nz, and then filling them with cubes that have a volume of 1. So each cube at the edge, at the corner of each one of those cubes, this first cube that we place right at the origin, at this edge is going to have a coordinate set of x equals 1, y equals 1, z equals 1. So that cube, we're going to say, represents the quantum state 1, 1, 1. Well, we could pack more cubes into this coordinate system, and every time we put a cube in, that corresponds to one quantum state. So what that says is if we now calculate a volume, now this is not a physical volume, this is a volume in this nx, ny, nz coordinate system, but the volume in this particular coordinate system will tell us how many states we have. Now the energy here, I guess we started from here, right? The energy formula that we had reached on the previous page said the energy was proportional to little n. In this coordinate system, n corresponds to the radius of a sphere. So if we were going to start putting photons into these different states and think in terms of how many quantum states do we have at a particular energy, what we could do is say that the number of states we have is equal to the volume that we've calculated here. And the volume is going to be spherical. Think of this as adding a bunch of spherical layers. Every time we add a new spherical layer into this coordinate system, that spherical layer will correspond to all the quantum states that have pretty much the same energy, pretty much the same value of n. Now you can see, because we're working in 3 dimensions, we have 3 quantum numbers. As we add each additional spherical surface, there's more and more surface area, which means more and more volume. Each layer has more volume than the one before it, which means there are more and more quantum states as we go up in energy. So instead of, every time we go up in energy we have one more state, what this is showing is that we're going to have many more states. As we go up in terms of energy, the number of states is going to go up. And, through physics 4b and 4c, I have repeated, I guess, this idea of more energy means more options for the molecules, or this time, for the photons. And that's what we're seeing. There are more and more quantum states available to the photons as we move towards higher and higher energy. And the way that happens is heating up the surface of the container. So if the container is at a higher temperature, then there are going to be more and more photons able to populate these high energy quantum states. Now, instead of using a container like this, you can kind of flip this inside out and think of this as, it's kind of like the sun or a star. If you look at the outer layers of the star, the photons in there are colliding with atoms and molecules frequently enough that it's almost as if they're inside a container. Now, if you're in a star, the photons aren't in equilibrium with the walls of the container. Instead, they're in equilibrium with the gas molecules at the surface of the star. But it creates the same effect. What happens is the photons reach an equilibrium distribution. There are some number of quantum states available. Those quantum states are populated in a manner that we can predict statistically, so we can use some statistics. If we know the temperature of the gas molecules, we can know how many photons are going to be radiated by those gas molecules, and the population of each of those quantum states then can be calculated, and that's how we derive the Planck distribution of photons generated in a region of space. Okay, So we've got the number of states is equal to, now we're only using a positive region for the quantum numbers, so we're really only doing 1/8 of a sphere. Now it turns out that, an aside here, is that photons have two spin states. You may be aware that electrons have two spin states. We call those spin up and spin down. Well, photons also have two spin states. They have an intrinsic angular momentum. And that means that each one of these quantum states that we define, you could have a photon spin up or spin down, helicity left, helicity right, within that same quantum, within the quantum state. So there's actually two quantum states at each energy that we come up with. So two spin states, and then finally that's just the volume of a sphere. So by the time we have counted possible quantum states all the way up to an energy level of little n, the number of states we have at that point is pi/3 times n cubed. So we can flip this equation around and say, all right, then little n is equal to 3/pi to the 1/3 power, n to the 1/3 power, and what we have done is, instead of that complicated counting method that we were using, 111, 121, 112, 211, now what we've done is we've replaced it with a set of quantum states that just count, like regular counting. 1, 2, 3, 4, 5, 6, 7. Now what you're thinking is, well, wait a minute, you're not going to get all the energies exactly right, and that's true. So when we make this conversion and write the energies in terms of big N, the advantage that we've created is now we can just count off the number of quantum states ordinally. Now, we're not going to get all the energies exactly right, but it turns out we do get the number of quantum states right, so we count every last quantum state, and the approximations are pretty good with the values that we come up with for these energies. So it gives us a very, very good approximation to the set of quantum states that would actually exist. So it allows us to take a complicated set of nx, ny's, and nz's, and instead of working in terms of this, which definitely is an easier formula, we've replaced it with this. So we've taken where there was a little n and replaced it with 3/pi to the 1/3, n to the 1/3. Now what we also do at the same time is we take L and replace that with volume to the 1/3. We might as well switch everything over into volume units, and so this becomes n/v to the 1/3. So we still have our factor of hc/2. We have this new factor of 3/pi to the 1/3, which came from counting all the quantum states. And then we have this new quantum number that's going to be much easier to work with. All right, now here's the rest of the steps. So we're at this point, we've come up with this new energy formula. What we do is we flip this around, and instead of saying energy as a function of the quantum number, we say that for a given energy, we can calculate what the quantum number would be. So by the time we've reached a certain energy photon, how many quantum states, or certain energy quantum state, how many quantum states have we counted through? And we can calculate it from this formula. Now this step is differentiating both sides. So instead of thinking in terms of n, the total number of quantum states, what this says is for every short interval of energy, imagine starting at the lowest energy quantum states and moving up a little bit of energy at a time. Every time we go up a little bit in terms of energy, we will add on an additional number of states, and that gets represented by dn. This is what's referred to as the density of states. It's an important calculation, an important quantum mechanical calculation that you guys are going to see for sure in your upper division classes or material science classes. This is going to show up somewhere. And it will also show up in chapter 40. So we also are going to be looking at this again in the near future. In chapter 40, we'll bring this back out as a way to calculate electron quantum states in metals. So this is what we use as a model for how the electrons are arranged in metal. Now, the formula we use for electrons won't quite be the same because we're not going to start with the relativistic formula, and we're going to use classical kinetic energies instead. So we'll see that the density of states expression, this is for photons. When we do this in chapter 40 for electrons, it's going to look a little different. So here's the steps. So we're almost to the Planck distribution. There's just a couple more steps we have to take here. First of all, let's say step one is what we've done, and that is telling us the number of quantum states for each energy interval. I should have written interval on here, I guess. I wrote it as per energy. Interval would be good. Now, statistically, we can go in and use what's called statistical mechanics and show that for a particular temperature, there is a certain number of photons that will populate each state. So the number of photons populating each one of these quantum states is 1 over e to the e over kt minus 1. So that gets multiplied by this number dn. So at this stage, we're counting number of quantum states, but at this stage, we're counting number of photons. So how many photons are there per energy interval? And then what we can do is move on towards intensity. So now it's not how many photons, but how much energy do those photons possess. Now, to convert from numbers into energy, and I wrote this as an internal energy, du, is equal to the energy of the photons at that level times dn, and that introduces one more factor of energy. So now, this new and improved version of our Planck distribution, it's not just counting photons, but it's counting how much photon energy is within a certain energy interval. Okay, one more step, maybe two. So here's the formula that we left with on the page before. So now we have du dE, how much energy is contained in all the photons within a narrow range of photon energies. And then the last step is what we call a rate factor. If you remember when we were looking at these Planck distributions, we were coming up with a distribution that said if we open up a small opening in the container and we have these photons flooding out and we send them through a diffraction grating and we measure where they are on a spectrum and what the intensity is at each wavelength. There's a rate factor that says if we start with the energy contained inside, kind of an energy density, that the intensity of the light coming out picks up a factor of C over 4. Now, if anybody wants to see this, stop by office hours and we can go over the derivation of this. It's a geometric factor that takes into account photons traveling in all possible directions. So it's kind of averaging over the angular distribution of photons. And it's kind of remarkable that the formula is really this simple, but this tells us the rate. So now we've gone from basically what would be an internal energy, what's the energy of all the photons, into an intensity. What is the rate at which energy is coming out per area? Now again, if we use a star as an example here, what's going on in a star? Well, the photons get generated in the outer layers of a star. And in that sense, it's as if they're still inside the container. But what happens is, some of those photons that are near the surface, within 100 kilometers or a couple hundred kilometers of the surface, there is now the possibility that they're not going to run into anything else, and as a result, they leave the star. So in those outer layers, in the inner layers, nothing is going to be able to reach the surface. It's going to run into something. But once you get closer and closer to the edge, now it's more and more likely that a photon that gets generated, traveling in a direction towards the surface of the star will actually leave the star. So when we think of the sunlight or the starlight coming out, it's those photons that leaked out the edges of the star instead of interacting with the gas molecules. So again, the same formulas apply for the light being generated in those outer layers of a star. The photons have plenty of time to reach equilibrium, the distribution that we're looking at, this equilibrium distribution, and then some of the photons are leaking out from the star, okay? Because they just don't run into a gas molecule that returns them back into the star. Anyway, the formula we end up with is this, and if you go back and check with the energy formula that we had derived in chapter 37, that's it. So we feel like, at this point, we understand a full derivation of the Planck distribution formula. And again, it comes down to counting quantum states. So it goes back to the energy and momentum operators. What are the possible quantum states? What are their energies? And then finding out what those distribution of quantum states look like, populating them with photons. I guess this is worth bringing up too. So it's always nice to make these comparisons, right? What applies to photons, what's going to apply to electrons. Electrons all need their own quantum state. So for electrons, the population of each quantum state is either 0, the quantum state is either empty, or there is an electron in that state. It's either 0 or 1. But for photons, typically there's going to be multiple photons in each one of these quantum states. And so this number of photons factor is different. There's also a number of electrons factor that we'll see in chapter 40. And the number of electrons factor runs between 0 and 1. Whereas this number could become really, really large, depending on which energy level you're looking at. As you go to lower and lower energies, you're going to have lots and lots of photons in those quantum states. Okay. All right. So in some ways, this was, I really wanted to do this example because it's a good chance to compare photons and electrons. It's a chance to see how quantum mechanics allows us to completely derive the Planck distribution formula that we started with back in chapter 37. Okay, again, I'm not going to be asking this stuff on the mid. I'm not going to be asking details of this on the midterm. I could certainly go in and ask questions about the Planck distribution, but you guys have seen the homework problems, so it wouldn't be anything different from items that we've seen in the homework or in the examples that we've looked at in the lectures. All right, let's move on. There's another, what I'm going to say is an important example that I hope we have time to look at all this. I think we do. This is what's called the quantum harmonic oscillator. So this starts out with an object with, well, two objects with mass m1 and m2 connected with a spring, an ideal spring. And then what happens is, classically, you would have these masses oscillating back and forth around the center of mass. Well, the potential energy of this system would be 1/2 kx squared, where x is keeping track of displacements from equilibrium. So if I settle everything down here and just have m1 and m2 sitting there at rest, now again I'm thinking of physics 4a, not physics 4c, because we know in physics 4c there never is a zero kinetic energy state, right? There's always a little bit of energy going on, it seems. That's going to be very likely. And that is what we're going to find, is that there's always going to be some kinetic energy at the level of atoms and molecules. Now the potential energy, 1/2 kx squared, where x represents displacements from equilibrium. So if we start with these two masses at a equilibrium distance, x would mean that there's a little bit of a stretch or there's a little bit of a shortening. We're either stretching the spring out or we're compressing the spring. X is telling us by how much. Now, this model that we've introduced, we're actually going to use that to identify quantum states of vibrational energy. So back in physics 4b, we looked at internal energies of molecules, and we said that for diatomic molecules, there were translational, rotational, and vibrational internal energies. Well, this is the vibrational one. So for a molecule, vibrational energy corresponds to the nuclei moving back and forth inside the electrons which are surrounding them. So again, the nuclei are going to be like point charges inside this really spread out negative charge distribution called the electrons. And those nuclei have most of the mass, 99.9 plus % of the mass is in the nuclei. So those nuclei can shift back and forth. And that corresponds to vibrational energy. Now, this is quantum mechanics, right? So it says, unlike classical physics, there's not a trajectory. It's not like we can actually write down some formulas and watch these nuclei vibrate back and forth. Instead, there's going to be a wave function describing what are the possible distances that the nuclei could be away from each other. So the equilibrium distance between the nuclei would represent a bond length, a chemical bond length, and variations in that are amplitudes of vibration, variations, and we'll have some kind of a probability distribution as far as how far the two nuclei are away from each other. So again, it's going to be a probability distribution. It's not going to be a trajectory that we can follow. All right, so for that, we're going to use the Schrödinger equation. We're going to put in a potential energy. It's going to be 1/2 ki squared. And then I'm going to say is the really important feature here is that we're going to introduce a potential energy expression. The kinetic energy, now we've got two kinetic energies to keep track of. So I'm going to write this as p squared over 2m and p squared over 2m1 and p squared over 2m2. The kinetic energy of nucleus 1 and the kinetic energy of nucleus 2. Now, since we're working in the center of mass system, it says that the system as a whole contains no momentum. And the momentum of object 1 and object 2 are going to be equal and opposite. So that means that I can write momentum 1 and momentum 2 just as momentum. They're going to have the same amount of momentum. So we combine those using this formula, 1 over 2m1 plus 1 over 2m2 times momentum squared. And so in order to bring this back so it looks like a typical kinetic energy formula, we're going to introduce what's called the reduced mass. 1 over the reduced mass, and for that we're using a Greek symbol mu. 1 over mu is equal to 1 over m1 plus 1 over m2. We just have to know the masses of the two nuclei and then plug them into the formula and see what we get for a reduced mass. Now the reduced mass is always less than the mass of m1 or m2. It's going to be even lower, so reduced mass is a good name for this. And as long as we're just looking at one chemical bond, we're looking at diatomic molecules. Now when you get to polyatomic molecules, the vibrational modes get more complicated, but they still follow the same basic pattern. And that basic pattern is that you identify all the different ways in which the nuclei could be shifting back and forth, in which the bond lengths could be varying, and those are vibrations. Those correspond to vibrational energies. So here is a possible solution, and this is actually, so we've set up the Schrödinger equation. Here is the energy times some wave function of x. Here is the kinetic energy term, and it's keeping track of both kinetic energies for object 1 and 2. It looks very similar. H bar squared over 2m, instead of the individual masses, it's the reduced mass. And then here is the potential energy term. Now it does turn out that the lowest energy quantum state for this quantized vibrational energy is this. So I've listed this as a possible solution. it is the solution. So this is actually one of the homework problems for the chapter. I think it's the last one or next to last one. It's near the end. And they give you this. I'm putting it in a slightly different format. I'm writing this as x squared over 2a squared for the wave function, and that means that the probability distribution becomes e to the minus x squared over 2a. Now, these functions are normal functions or Gaussian functions. We saw these before when we were looking at wave packets. These mathematical expressions turn out to also be solutions to the Schrodinger equation for a potential energy of 1/2 kx squared. Okay? So let's plug them in and see how this works. So here's the wave function, here's the first derivative, here is the second derivative. By the time I got the second derivative, I can plug that back in to the Schrodinger. So here's the Schrodinger equation right here. There's the potential energy term. Here are the kinetic energy terms that we got by taking the second derivative, multiplying by h bar squared over 2m, or 2 mu in this case. And then here is the energy times the wave function. Now, the wave functions cancel out, and we are left with an equation that looks like this. Now, what we've done, or what we're in the process of doing here, is solving for solving a differential equation. We're taking a possible solution and verifying that it satisfies the requirements of the differential equation. Now, the function itself, if you notice, it drops off exponentially as we move away from the x equals 0 value. And that's important because we need to be able to normalize this. So this is normalizable, which means that there's a probability of 1 of the bond length having some value, and that the most extreme values are going to become very, very unlikely. Now, when we get to this stage in the differential, solving the differential equation, what we can see is I have a constant e, which I'm trying to evaluate, and then there's another constant that came from this term in the kinetic energy, h bar squared over 2 mu a squared, and then this term came also from the kinetic energy, and it has an x squared in it, and then finally the potential energy term has an x squared. Now, in order for this to be a solution, this equation has to be satisfied for all values of x. The only way that's going to be possible is if the two constant terms are set equal to each other and the two x squared terms are set equal to each other. Everything here has to cancel out. So there's two conditions that need to be met. And the first one is that the constant terms need to exactly balance out, and the two x squared terms need to cancel out exactly. So I've just set their coefficients equal. So here's what the diagrams, the energy diagrams, look like. Here is no energy at all. Now, I've labeled these as state 1 and state 2. When we come back in chapter 40 and look at this one more time with diatomic molecules, they're going to relabel these as state 0 and state 1, but that's not important right now. So I'm going to say this is quantum state 1, the lowest energy quantum state. This is quantum state 2. This is what the wave functions look like, and this is the probability distribution. Now, what you're seeing with the wave functions and the probability distributions is there's some real similarities between what we're seeing with the harmonic oscillator potential energy to what we saw with the infinite potential well. Now, with the infinite potential well, there were limits set by the infinite potential on either side that were firm limits. The wave function had to go right to 0 at those locations. These are soft limits. The potential energy goes up, but it doesn't go to infinity. And so the wave function extends out beyond the potential energy region. So rather than having it go right to 0, it's going to drop off exponentially. So we're going to have a wave function or a probability distribution that looks something like this. Now, for the second wave function, there's going to be a node in the middle. Same thing that we saw with the infinite potential well. And so when we look at probability distributions in that lowest energy vibrational state, the most likely distances between the two nuclei is the average bond length. You know, the bond length that you would look up in a table turns out to be the most likely, and then you can see how the probabilities drop off as we stretch out the bond a little bit or as we compress the bond a little bit, shorten it. Notice though in the first excited state, this is kind of interesting, there is no probability of being at the bond length. The probability, there's two regions of high probability. One of those is where the chemical bond is a little longer than its bond length, and the other one is where it's a little shorter. Now it averages out to being the bond length that you would look up in a table, but this probability distribution says that no, you're not going to ever find it right at the average bond length. So that's always these interesting predictions from quantum physics, and they play out, or they pan out, in that when we do experiments we find out this accurately describes these states. So I wrote down the conditions here. Here is a to the fourth needs to be equal to h bar squared over mu k. Now what this is saying, this is important I think, is that if k is larger, if the bond is stiff, you know, if it's a stiff chemical bond, that spring is really stiff, then A is going to be less. We will not see much floppiness in the bond length if the chemical bond is very stiff. Now, what makes for a stiff chemical bond? I picked out a couple of compounds, oxygen and nitrogen, O2 and N2, that have especially stiff chemical bonds, and N2 in particular has one of the stiffest chemical bonds. Now, if you've seen these in chemistry classes, you're thinking, oh yeah, that's a double bond, and nitrogen is a triple bond. And they're also small, relatively small atoms. So relatively small atoms with multiple bonds tend to be really stiff, and that means that you don't get much amplitude of vibration. The nuclei can't shift back and forth very much because the potential energy will change very rapidly if the nuclei shift back and forth too far within the surrounding electron distribution. So that's how we would go in and calculate A. This was just a diagram showing what that indicates. A is a scaling factor. It's going to be measured in picometers, probably, if we're looking at atoms and molecules. And it tells us kind of, you know, what's a typical range of amplitude for the chemical bond. Now, the energy, and this is just quantum state 1 that we're looking at, I plugged or algebraically plugged into a squared here, and ended up with this formula, 1/2 h bar k over mu, where k is the bond stiffness and mu is the reduced mass. So we can calculate how much energy there is at these different quantum states, or at least for quantum state 1. We haven't got the general formula. We'll come back in chapter 40 and look at that. But right now we do have an energy for quantum state number 1, the lowest one. Yeah, and so let's go ahead and look at some numbers for O2 and N2. I guess we're starting with nitrogen. So here's a diagram saying there's 2 nitrogen nuclei, and they're vibrating, or they're shifting. There's a variable bond length, R. The bond length starts out, the average bond length is 109 picometers. And then I also looked at the bond energy. Now the bond energy says if we can come up with 9.79 eV, we can dissociate the molecule. We can separate it into 2 nitrogen atoms. So if the vibrational energy gets too large, the molecule could come apart. Okay, that's good to know if we get too much vibrational energy. So I went through and I calculated the reduced mass and converted that into kilograms. From that, let's see, what else do we need to calculate here? I have the bond stiffness. I plugged into this equation, I got the reduced mass, and calculated what the amplitude of vibration would be. And it came out at 4.5 picometers. So it's got a bond length of 109 picometers, plus or minus 4.5, at least in vibrational state 1. If I go to an excited state, that amplitude is going to go up. So this is the average bond length, and this is how much variation we see in the lowest possible vibrational energy state. And yes, the lowest possible state already has energy in it. There's no such thing as zero vibrational energy in a molecule. Every chemical bond is going to have some vibrational energy associated with it. It's not going to be zero. That bond length is not going to be fixed at some value. Now, the energy that I calculated, we can introduce what's called a frequency of vibration. It's a little artificial, but it's a useful intermediate step. We can calculate that as k over mu to the 1/2. So that came out in radians per second. And then I plugged into the energy formula. Turns out that the energy of the lowest vibrational state is 0.164 eV. Now compare that with the bond energy. If we continue to go up in vibrational energy states, it's possible, I guess, if we keep going up in steps about this size, eventually the molecule could come apart, right? Eventually we exceed that limit of 9.79 eV, and the vibration energy now is enough that the molecule just separates. We can run the same numbers for oxygen. Here the bond energy is 5.15. Again, this is a double bond instead of a triple bond. I put this in eV and in kilojoules per mole. I know that chemistry textbooks like to work in kilojoules per mole. It turns out that 1 eV of bond energy is very, to a good approximation is 100 kilojoules per mole. So if you're looking in your chemistry textbook and writing down those numbers for how many kilojoules per mole, for every 100 kilojoules per mole, that's about 1 eV. So you can start looking at chemical bonds in chemistry and thinking in terms of individual bonds, in terms of eV, which are units that we're looking at all the time. Now again, by looking at these in eV, then you can say, okay, if a photon of light comes in with, well, in this case, we're back at nitrogen. If a photon came in with 10 eV, that would be enough to separate this into 2 nitrogen atoms. For oxygen, that number is only 5 eV. Now that would be in the ultraviolet, but that's how you can think of these bond energies, is if a photon came in with 5.15 eV, that's enough energy that the molecule could separate into 2 individual oxygen atoms. All right, the bond stiffness here was 1133. It's only about half of what it was in nitrogen. And as a result, we're seeing amplitude of vibration for the lowest energy state. That's 5.21. I should have put a subscript 1 on this to point out that we're really just looking at the first vibrational state. So we're going to see a bond length of 121, plus or minus 5.2 picometers. And again, I drew this little probability distribution. The energy calculation ended up at 0.096 eV. So the spacing of the energy states looks like it's going to be closer. So that's only about half as much energy as we saw for nitrogen. But, the bond energy is only about half as much. And that means that in the O2 system also, once we get up to a high enough vibrational energy state, the molecule could just come apart because of vibration. All right, so those are some good examples, I think, to take a look at. Now, we just have a couple minutes here. In fact, maybe we're going to take a few extra minutes to finish up some later topics in the chapter. We're not going to really use any of these in a lot of detail, but this is what's called a finite potential well, and that says that a particle is sort of confined inside this region, but outside is not infinite. And so what happens in this case, here's the Schrödinger equation, is that we put in a finite value of the potential And the value inside is different from the value outside. So if we go back here, what we're saying is that when we head outside, we have to allow for this potential energy, but inside we don't. So we actually have two different Schrodinger equations, one with the potential energy for the outer regions, and one with not the potential energy for the inner region. And then we have to match up the derivatives. There's a lot of math involved here, but again, we're not going to look at the derivations. We are only going to be looking at what happens to the wave functions. And if I look at wave function 1, 2, and 3 now, instead of a boundary condition where the wave function has to go right to 0 at the edge, now the wave function extends outside of that region. And that's it. That's what happens when you relax the conditions of the potential energy, is that now some of the wave function is outside. That means some of the probability is actually in a region where it doesn't have enough energy. Classically, we would say, well, if this were an electron, for example, it just doesn't have enough energy to be in this outer region, but quantum mechanics allows some probability to extend out beyond where we would expect to see it. Kind of a surprising prediction from quantum mechanics. Now, if this outer region is actually only a finite barrier, so in this case, I've got, let's say, an electron inside here, but there's another region of low potential energy over here. Well, the wave function actually allows that there's some possibility that the electron passes through the barrier and finds itself on the other side. So as time goes on, eventually the probability of the electron being in this region could go up. It could go up to where it's just as likely to be over here as it is over here. Or if it's a traveling electron, if it's an electron that's coming along with a certain amount of kinetic energy, there is going to be some probability that it goes through the barrier. Okay, so this is really important in circuitry. When we're looking at transistors or diodes or microchips, really, when you're looking at chips that have millions of transistors manufactured right on the chip, these barriers are layers of insulating material that can be placed down. So you can put alternating layers of materials into these chips, and you can create these processing effects where some portion of the current makes its way through, maybe some of the current gets reflected back in the direction that it came from. So it's an important concept. Now, they go through the book and they derive some formulas for us, and we're not going to go through the details of those, but here is an example. There's a formula right here, I guess. So here's the formulas they derive. They go, what are the chances? What's the probability of transmission of the electron passing through to the other side? And we can calculate that by plugging the numbers in. And I'm going to go ahead and wrap things up here. So what's the probability of the electron passing through a barrier? Now, they're saying the electron comes in with 50 eV of kinetic energy, and the barrier is 70 eV. So it doesn't have enough kinetic energy to pass through the barrier classically. But quantum mechanics says because it's a wave function representing the particle, the wave function will only drop down exponentially. It won't suddenly drop to 0, even if the barrier is more energy than kinetic energy the electron has. And they have us first calculate this with a nanometer wide layer of material. How is the electron going to be able to get through? And then they switch it down to 0.10. So I went through and plugged the numbers in. I solved for, here is what calculating G looks like. Plugged in the mass of the electron, the difference between the barriers. Now, let's go back and take a look at this. So here, they say that the barriers are 50 EV and 70 EV. Those seemed like pretty large barriers, so I scaled them down. So I said that the energy of the electron, the kinetic energy, is 5 eV, and the barrier is 7. So I did put some different numbers in. And then I calculated what G would be for the electron. And then I plugged it into this formula. Now the G value doesn't change when we change the length. The length is a separate factor here. And what I ended up with was, for a thickness of 1 full nanometer, there's only one chance in 2 million that the electron coming in would cross the barrier. Well, if I've got a current of 1 amp or something, or 2 amps, I'm going to have a millionth of an amp that gets through. So we are going to have something measurable. Now, if we shorten the thickness from 1 nanometer to 10, this is an exponential effect. So I'm reducing this by a factor of 10, and now the transmission probability is 23%. So it's almost 1/4 versus 1/2 millionth. So we can manufacture these materials, or these transistors and such, in a way where they're going to have different transmission properties to them. All right, and then there's some examples here of an electron tunneling scope. And then that's it. Ooh, I thought there were more examples, but we are through here. So that's kind of everything we looked at. Again, the important items, or the items that we've really looked at. Here's the Heisenberg uncertainty. We did do a number of examples with these. Take a look at it. I don't feel like these are going to be as important as the later parts of the chapter. So having an idea how to set up these Schrodinger equations, solving for the infinite potential well in 1 dimension, solving for the infinite potential well in 3 dimensions, as well as looking at the harmonic oscillator example. Those are going to be more important. So those are the things you really want to make sure you have down well. All right, so I guess the midterm's coming up. We'll have a review session for the next lecture, and then we'll have the midterm. So, office hours are there. Stop by with whatever questions you've got.